Welcome to Scholarly Snapshots, the channel that makes peer-reviewed research accessible. In this video, we will be discussing the phenomenon of learned helplessness, which was discovered 50 years ago. We will explore the original theory proposed by Seligman and Maier in 1967 and how the author's understanding of the phenomenon has evolved over 50 years of research. Learned helplessness is a phenomenon where animals learn that they cannot control aversive events, and therefore stop trying to escape them. The article we will be summarizing outlines how the passive response to shock is not learned, but is a default response to prolonged aversive events mediated by the serotonergic activity of the dorsal raphe nucleus. The research began with dogs but shifted to rodents, using the same triadic design that compares equal escape, yoked inescapable, and no shock. Studies showed that inescapable shock leads to behavioral changes such as reduced aggression, reduced food intake, and increased anxiety. The research also tested alternative hypotheses about why learned helplessness occurs, with most of the focus on why inescapable shock produces failure to learn to escape rather than why escapable shock did not. The article discusses the neural basis of learned helplessness and mentions the work of J. Weiss, who showed that inescapable shock depletes norepinephrine, NE, in the region of the locus coeruleus, LC, a brainstem cell cluster that provides NE to most of the forebrain. The authors propose a new theory which suggests that passivity and anxiety are caused by prolonged exposure to aversive stimulation, and that the presence of control, not the absence of control, is detected by prelimbic medial prefrontal circuits. The research uses rats as subjects, and the response that the ESC subjects can perform to terminate each shock is the turning of a small wheel located on the front of the chamber. The article explains the passivity, anxiety in the dorsal raphe nucleus, and the role of serotonin, 5-HT, in the dorsal raphe nucleus that projects to both, inhibiting one and potentiating the other when it is activated. The study suggests that DRN activation is necessary for producing passivity and anxiety, but its sufficiency can be achieved by activating the DRN by microinjecting agents. Furthermore, the article explores the question of how DRN detects the uncontrollability of the shock and what inputs inform DRN of this information. In conclusion, the article discusses the neural mechanisms underlying the perception of control over stressor, and how control could be detected by a different circuit, with the information conveyed over to the ventromedial prefrontal cortex. We hope you enjoyed learning something new today and that our simplified summary helped you understand the research a little better. Thank you for watching, and we'll see you in the next episode. Thanks for watching.